Now we're going to look at sampling, about the aliasing part, because right now we have stored our data at some points. And those points I will draw because right now we do not know what the original function looked like. Of course, a stem here. Another one down here, or up here. Somewhat like this. And we have these values, which is nice and all, which came from our function 3 times the cosine of 6 pi t minus pi. And we right now want to know what function actually fits these data points. And we are trying to find the smallest positive frequency for which these points are correct. And that is called the principal alias. So we have our principal alias denoted by omega 0 hat. And this is the smallest frequency. So the smallest obtainable frequency from these dots. If it is not the smallest one, it's called a folded alias. And possible reconstructed formulas then look like a times the cosine of plus or negative, the positive or negative part of omega hat 0 plus 2 pi times L. I need another bracket here. Times n plus, so the positive or negative part of phi. And the L, what it is doing there, the L is from the integer set, so it can be all positive and negative whole values. That means that if we up the frequency with 2 pi, then we get another signal which also goes to these points, but has one more period in between points, and that we will draw later on as well for a better visual understanding. But still, our question is, we have these dots in our graph here. We have plotted those, but what is actually the best sampling period to take, the best sampling frequency? And for that, we have to go to Shannon, namely Claude Shannon, who has developed a theory, and he lived from 1916 until 2001. And he developed a theory, namely Shannon's sampling theorem. And this is also an important one. It's not that difficult. What he says is that if we have a sampling frequency, then we want to know what the best frequency is, and it should be at least, or excluded, what the boundary. So the sampling frequency must be higher than 2 times the maximal frequency in the spectrum. And this exact value is called the Nyquist rate. Nyquist rate. If it is not, if the sampling frequency is lower, then we will not be able to construct that higher frequency, because we will always assume the lowest frequency is the best one. That's why you always see on CDs that the highest, the sampling frequency is 44.1 kHz or something, because it is twice the hertz range that we humans can hear, about 20,000, 22,050 or something. So if we do not take a sampling frequency that is high enough, we will run into problems. And if it is exactly the boundary, we have some other complications, for which I will show you for our own function. So we had a function of 3 times the cosine of 6 pi n minus pi. Well, if we have 3 scenarios. Scenario 1 is where our sampling frequency is indeed higher than the highest frequency in our function. This is also called oversampling. So let's say we have a sampling of 12 Hertz. Then our omega hat is 6 pi divided by 12 is pi over 2. Well, our omega hat is in between negative pi and positive pi. So that means that the sampling period or sampling frequency that we have chosen will be good enough to get the highest possible frequency. So we know that omega hat is our omega hat 0. That's good. So we have a good reconstruction. The function, the actual function that we give, the 3 times cosine 6 pi n minus pi, we will obtain. Oh, sorry, this should be a t. Excuse me. So we will get the exact function back. Now, if our sampling frequency is exactly 2 times the maximum, we will get some complications. Our sampling period is, for example, 6 Hertz. Then our omega hat will be equal to 6 pi divided by 6, which is pi. Our omega hat is exactly on the boundary of pi. And that is a problem. Because while we will get our frequency back, so this results in our original frequency, however, we do not know the amplitude. So you get a times the cosine of 6 pi t minus pi. But we never know a. And why is that? Well, let me show you what happens if we have something like that. So we have our points right here. One below here. Then we have one up here. One below here. Oh, again, etc. So one way our function could go is like this. Kind of like that. But another possible way for our function to traverse this is like this. Like that. So the period may be the same, but the amplitude can be all over the place. We do not know the actual amplitude. So this also kind of gives a problem. So we want to sample with enough frequency bandwidth, or enough frequency sampling to get all the frequencies in our spectrum. So let's try that for the next one. We have a frequency that is lower than 2 times the maximum frequency. This is also called undersampling, which gives us the most problems. So suppose we have a sampling frequency of 4 Hertz. Then our omega hat is 6 pi divided by 4, which is 3 over 2 pi. Well, because 3 over 2 pi, or our omega hat, is not between these boundaries, we can actually subtract 2 pi from it. So we get 3 over 2 pi minus 2 pi, which is minus pi over 2. Well, this is great because minus pi over 2 is indeed in these boundaries. So we get our function, reconstructed function of 3 times the cosine of minus 2 pi t minus pi. And this, of course, gives us problems. If we draw the plot, then we would have some points here. Something like this, where our actual function, which I will draw with purple, will be going something like this. Like that, but the actual constructed function that we obtain will go like this, because this is the function we can reconstruct with the lowest possible frequency that can pass through these points. So we actually lose information here, and that is also something that you can see for yourself. If you videotape something, you listen to the audio, then you hear something normally. But when you slow it down, because there's not enough sampling in between all these values, the frequencies just get stretched. That's why every voice gets lower. But if you sample more and more per second, then actually when you slow down the video, the voices will stay the same, but just slower, because you've sampled more. Well, if you want to know how to obtain actually this phase, and not this one, this phase in our cosine and here as well, we actually did not know that. But how to reconstruct our functions perfectly with the phase and everything, we need pulse functions. And for pulse functions, we have our next video.